Hi everybody, I hope this video finds you well. In this video we're going to be continuing on with section 3.2 talking about the properties of the determinant. This video is going to focus mostly on one really sort of important theorem, tying together the concept of the determinant and an earlier concept which was the invertibility of a square matrix. So we sort of said one of the main ideas about why we built this determinant is to have something that basically, if you'll sort of pardon the pun, determines whether or not a square matrix is going to be invertible. And this theorem sort of ties those two things together. So what this theorem says is we're going to let A be n by n, then A is invertible, so in other words, A has an inverse, if and only if the determinant of A is non-zero. So it says that if a matrix is invertible, then its determinant is non-zero. Furthermore, it says that if the determinant is non-zero, then the matrix is invertible. This is an if and only if. Now, since it is an if and only if, right, not only do you get the two directions here, namely saying that if something is invertible, then its determinant is non-zero, and if the determinant is non-zero, then it is invertible, you also get the two converses, meaning that if something is not invertible, its determinant will be zero, and if something has a determinant of zero, then it will not be invertible. So that's the benefit of an if and only if statement. All directions apply here. So we are going to prove this real quick and then look at a couple examples of this. To prove this, we actually have to do two separate parts, right? We have to show both directions of this if and only if. So for the first proof, we're going to do this direction. So we're going to assume A is invertible. And what we need to do is we need to show that the determinant of A is not equal to zero. So how are we going to do this? Well, let's think about what we know when A is invertible. Well, when A is invertible, we know it has an inverse. So we could talk about A inverse. But A inverse, we don't know anything really about the determinant of the inverse, so that's not going to necessarily help us. Instead, we want to think more fundamentally about what it means for A to be invertible. Remember, A is invertible if it is row equivalent to the identity matrix. So A is invertible implies that A is row equivalent to the identity. Remember, when we use that little squiggly line, we mean row equivalent. Certainly does not mean that these are equal, but it means that they are row equivalent. Okay, now, if you remember, right, when we sort of discussed the elementary row operations, each elementary row operation at most modifies the determinant by a scalar amount, right? Interchanging two rows negates the determinant. Multiplying a row by a scalar value, right, multiplies the determinant by that scalar value. And adding a multiple of one row to another row doesn't change the determinant at all. In other words, we sort of stated that if two matrices are row equivalent, then their determinants are off by at most a scalar multiple. So if we know that A is row equivalent to In, then we can say, right, this implies that the determinant of A is equal to some scalar times the determinant of the identity matrix, with C not being zero. Because of course, this multiple can't be zero, because what do the elementary row operations do? They either negate something, which definitely is not a constant of zero, or they multiply by a non-zero scalar. So when you put all that together, this has to be non-zero. But what do we know about the determinant of In? Well, the identity matrix is a matrix that is in a diagonal form. It's ones on the diagonal and everything else is zero. That means, according to the sort of very first theorem of section 3.2, the determinant of In has to be 1, because 1 times 1 times 1 on the diagonal is just 1. So this tells us that the determinant of A is C times 1, which means that the determinant of A is whatever that constant is, but with the knowledge that that constant is non-zero. So what have we shown here? Well, we've shown exactly what we wanted, that the determinant is not zero. So determinant of A not equal to 0. And there we go. Pretty easy to show that. We've just shown that if it is invertible, then the determinant is non-zero. Let's do the proof the other direction. So now we're going to prove this in reverse, right? So we're going to assume that the determinant of A equals 0. Okay, what we then need to show is that the determinant of A is not equal to 0. We need to show A is invertible. Okay, so we're doing the opposite direction here. Okay, so we've got that the determinant of A is not equal to 0. We need to show that A is invertible. All right, so to do this, right, let's think about this. Let's let A star be A in reduced row echelon form. Okay, so we're going to let A star be the matrix A in reduced row echelon form. In other words, if what we need to show is that if A is invertible, then all we really need to show is that A star is actually the identity. So we can rewrite our need to show that A star is equal to the identity. That should make sense, right? Because if A star is A in reduced row echelon form, then if we can show that A star is equal to IN, then we're basically saying that A is row equivalent to IN, which is the definition of being invertible. So we need to show that A star equals IN. Okay, so since A is definitely row equivalent to A star by definition, this implies that the determinant of A is equal to some constant times the determinant of A star. Still with that assumption that C is not equal to 0. And sorry for having to sort of put that above that, but there we go. Okay, now we know by assumption that the determinant of A is non-zero. So if we think about this, if C is non-zero and the determinant of A is non-zero, then this implies that the determinant of A star is not equal to 0. So this tells us that A star, which is the reduced row echelon form of A, also has a non-zero determinant. But what does A star need to look like? Well, A star, right, has to be in reduced row echelon form, meaning that every pivot position has to either have a 1 or be a 0. But if that's the case, and we know the determinant is not equal to 0, then that means that every pivot position must have a 1. So this implies every pivot in A star must be a 1. If any of the pivot positions were 0, then A star, because it's in reduced row echelon form, it's naturally upper triangular, it's actually naturally diagonal. If that's the case, and any of those pivot positions were 0, the determinant would be 0. But we know the determinant is non-zero. So every pivot in A star must be a 1. So that means A star has 1s on every pivot position, so 1s on the diagonal, and 0s elsewhere. That then tells us that A star is actually equal to IN. And that's all we needed to show. So this basically shows you guys that overall, invertibility and the determinant go hand in hand. If you want to diagnose if something is invertible or not, you can just directly calculate the determinant. So let's go ahead and look at a couple examples of doing that. So we're going to do 2 examples that sort of tie all the concepts that we've been discussing so far for square matrices together here. So as an example here, let's let A be this matrix. So we're going to let A be the matrix 2, 0, 5, 1, minus 3, 4, 4, negative 6, 13. And we're going to determine a couple things. We're going to determine the rank of A, the determinant of A, and A inverse, if it exists. Now, we've got a bunch of different things to do here. We want to calculate the rank, so we want to know when this guy is in row echelon form, how many non-zero rows do we have. We also want to get the determinant of A, and we want to know A inverse if it exists. What I want to do in this is not only show you guys how determinant and A inverse are sort of related and how that all relates back to rank, but also show you guys sort of an efficient way of doing this. Since we want to know A inverse, we are still going to take the time to augment this matrix with the identity, because our goal, if it does have an inverse, is to find that inverse. And while the determinant can tell you whether or not something is invertible, it does not actually tell you what that inverse is. So the first thing we're going to do is we're going to take our matrix 2, 0, 5, 1, negative 3, 4, 4, negative 6, 13. And we're going to augment with 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. All right, now as we begin to do sort of row operations on this in attempting to make it look like the identity, not only will we track what that does to the identity in hopes of finding A inverse, we will also track what that does to the determinant, so we can also calculate the determinant along the way. Basically, we're just sort of doing something so that we can do all three of these things simultaneously. So what would be a good sort of beginning? Well, you could divide through that top row by 2, but that might make things a little bit messy. So maybe it's better to interchange row 1 and row 2. So let's go ahead and do that. Let's interchange row 1 and row 2. So that's going to be 1, negative 3, 4, and then 0, 1, 0. Then 2, 0, 5, 1, 0, 0, and then of course the bottom, 4 minus 6, 13, 0, 0, 1. Okay. Now, let's also make a little law here. This guy over here has the determinant that we want. Well, what about this guy here? Well, since we interchange two rows, this guy actually has negative the determinant that we want. Okay, so we're going to basically keep track of this so that we can hopefully find the inverse, and also keep a track of this so we can find the determinant. All right, let's go ahead and do another operation. Now that we have this nice 1 here, we can clear out the stuff below it. So let's do row 2 and replace it with row 2 minus 2 row 1, and row 3 with row 3 minus 4 row 1. So upon doing that, we should have 1 minus 3, 4, and 0, 1, 0. Okay, nothing changes there. Here we're going to get 0, and then looks like 6, and then 5 minus 8, so negative 3. And then looks like we should get 1 minus 2, 0. And then in this guy, we should get 0. And then, what is that? Minus 6 plus 12, so 6. And then 13 minus 16, so minus 3. And then looks like we should get 0 minus 4, 1. This guy had negative the determinant A. These operations do not impact the determinant, so we get negative the determinant of A here as well, if we're keeping track of that. Okay, now, again, we could go ahead and divide everything through here by 6, but again, we should be able to sort of just recognize we can zero this entire row here just by directly using this guy. So let's go ahead and do that immediately. So I'll actually just do that on my next line here. So let's go ahead and do row 3 and replace it with row 3 minus row 2. All right, if we do that, we get 1 minus 3, 4, 0, 1, 0, 0, 6 minus 3, 1 minus 2, 0, and then here we should get 0, 0, 0, and then we're doing row 3 minus row 2, so it looks like we should get minus 1, minus 2, and 1 there. And of course, that operation also does not impact the determinant. All right now we can see some things here. Two things we can immediately recognize. One, it is going to be impossible to make this look like the identity because we have a 0 row. That tells us it's not invertible. Also, this thing is in upper triangular form. So what's the determinant of this? Well, it's just the multiplication of those diagonal elements. So 1, 6, and 0 is going to be 0. So negative the determinant of A is equal to 0. So the determinant of A is going to be 0. So right from here, we can tell a couple things. Right? This tells us A is not invertible. Also tells us negative the determinant of A is equal to 0, which implies that the determinant of A is equal to 0. These two things always go hand in hand. A being not invertible and the determinant of A being 0, these two things have to happen at the same time. Does this guy tell us the rank? Well, he's not technically in row echelon form here because there's a 6. But of course, dividing through by 6 isn't going to really change anything. He's already at least in upper triangular form, which is actually good enough for diagnosing rank. So we can actually also get the rank here. The rank of this guy is 2. So we can also get that the rank of A is equal to 2. How does the rank sort of tie in with these facts here? Well, remember that the way rank relates to invertibility is that your rank must be full. It must match the number of rows and columns if you're going to be invertible. In this case, we had a 3 by 3 matrix. The rank, however, is only 2. That's why we're getting something that's not invertible, and that's why we're getting a determinant that is 0. So notice all of this can be done sort of simultaneously as long as while you're tracking your row operations, you also track what happens to the determinant. All right, let's take a look at another example of trying this. There we go. Let's go ahead and give ourselves another example here. So let's let B be the matrix 1, 1, 0, 1, 0, 1, 0, 1, 2, 2, 1, 2, and 3, 3, 0, 4. So let's go ahead and see if we can, let's say, determine rank of B, the determinant of B, and B inverse, if it exists. Okay, so we've got this matrix here, and we're going to try to do the same three things, right? Rank of B, determinant of B, and B inverse. So let's start again by sort of augmenting this thing. 1, 1, 0, 1, 0, 1, 0, 1, 2, 2, 1, 2, 3, 3, 0, 4. And then we've got our identity 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay. So let's see what operations we can do. This time I think just because this is a relatively sort of large matrix here, we're actually going to go this way, and if necessary, maybe we can come back up here. So I'm going to actually write my row operations in between here. Sorry if it's a little bit messy there. Okay, so we like this guy here. We can use that to zero out down here. So let's just make a note. This guy has the determinant of A. So let's begin by taking row 3 and replacing it with row 3 minus 2 row 1. And row 4 with row 4 minus 3, row 1. So when we do that, we should get 1, 1, 0, 1, and then 1, 0, 0, 0, and then 0, 1, 0, 1, because we're not modifying anything, then 0, 1, 0, 0. Then we're doing row 3 minus 2 row 1 up here. So it looks like that should give us 0, 0, and then looks like a 1, and then what is that going to be? 2 minus 2, so that's going to be 0, so that's nice and easy. And then, of course, we are going to get that this guy should be minus 2, 0, 1, 0. There we go. And then down here, right, looks like we should get that that's going to be 0, 0, 0, 1. And then we should get minus 3, 0, 0, 1. Did that do anything to the determinant? Well, these are elementary row operations of the third type, so this keeps the determinant the same. All right, so now we can start cleaning up this stuff here. We can use this guy. We've already got it into sort of upper triangular form, so we can actually calculate the determinant right away, right? And it's just sort of a note here, right from here. We can get a couple things. We can get the determinant of A. Well, we know the determinant of A is 1 times 1 times 1 times 1. So we can immediately get that the determinant of A is 1. This guy is also in upper triangular or also in row echelon form. So we can get that the rank of A is equal to 4. Also notice that that tells us that the rank is full, right? So it's a 4 by 4 matrix and its rank is 4. So it is got a full rank. So we also know that A is invertible. Okay, if we were just interested about characteristics, we'd be done. But we actually, not A is invertible, my bad. And we should go back and catch those things. It's my mistake there, guys. That should be determinant of B. This guy should be determinant of B, and all of these things as well. So I named this guy B instead of A. So determinant of B, rank of B, and B is invertible. So if you're only interested in the characteristics of B, we would be done. We know its determinant is 1, which of course you should also note is non-zero. Its rank then is full, and it is invertible. But we actually want to know its inverse, so we need to finish up and actually take this thing and put it as identical to the identity. So let's go ahead and do that. We'll sort of follow this stuff up here. Looks like the first thing we should do is start back solving using this guy to clear out the stuff up here. So it looks like we'll need to replace row 1 with row 1 minus row 4. And we'll need to replace row 2 with row 2 minus row 4. Now again, we've already calculated the determinant, so we don't need to track that anymore. We're just trying to find the inverse here. So if we do that, looks like we should get 1, 1, 0, 0. And then of course, if we subtract there, looks like we should get a 4, and then 0, 0, minus 1. And we'll close that guy up. And then looks like we get 1, 0, 0, 0. And when we subtract there, looks like we should get 3, 1, 0, minus 1. And then we've got 0, 0, 1, 0. And then minus 2, 0, 1, 0. And then nothing changes down here either. 0, 0, 0, 1. Minus 3, 0, 0, 1. Okay. Last thing that's out of place here is this guy right here, but we can use this guy to sort of eliminate here. Notice we don't need to use this guy because these were already zeros. So we just need to use this here. So we'll just take row 1 and replace it with row 1 minus row 2. And when we do that, looks like we should get 1, 0, 0, 0. And we should get 1. And then looks like we should get 0, 0. And then minus 1, minus 1. So it looks like 1 there. Okay. Oh, my mistake. Sorry about that. Sort of lost track of exactly what I was looking at there. Okay, 0, minus 1. There's minus 1, 0, and 0. There we go. And then row 2 should stay the same. So 0, 1, 0, 0. 3, 1, 0, minus 1. 0, 0, 1, 0. Minus 2, 0, 1, 0. 0, 0, 0, 1. Minus 3, 0, 0, 1. So this tells us here that B inverse is actually the matrix 1, minus 1, 0, 0. 3, 1, 0, minus 1. Minus 2, 0, 1, 0. Minus 3, 0, 0, 1. And there we go. So we've determined B inverse. So along the way, we were able to figure out the determinant of B, the rank of B, and that B is invertible. And then, of course, we actually finished up and found the inverse of B in that process there. So there's a couple examples, sort of a relating determinant and rank and invertibility all together. Also just shows you guys sort of a nice way of keeping track of all that, sort of when you have to augment and keep track of the determinant. Just make sure you guys have, some sort of consistent notation to take care of all that. In the next video, we'll be finishing up 3.2, finishing up the properties of the determinant.